Welcome everybody. Sorry for the technical problems. So today we will start with the second part of exercises presented by Pablo Quilez. Okay,
yeah.
Pablo Quilez. So I think you can start because we have already some delay. So
okay, so good morning.
And feel free to interrupt the speaker anytime you wish, because these are exercises. So if there is something unclear, it's better that you ask immediately. Just unmute yourself.
Exactly. So good morning to everyone. And indeed, I would encourage you to stop me at any moment and ask me any questions. And in fact, in order to try to make this session a bit more interactive, I will keep asking you questions. So please keep with me and try to answer them so that we can not get too bored on a Friday morning, right? Okay, so today we're going to keep talking about axions, but in this case we're going to focus on how we can produce the axions in the early universe, right? Because as you have heard from the lectures of Andreas, we know that the axion is a good dark matter candidate. And in order for it to be a good dark matter candidate, we need to be able to produce it in the early universe, right? There needs to be some kind of production mechanism. And in particular, we will try to do some simple computations regarding one of these production mechanisms, that is the so-called misalignment mechanism. Okay, but before going there, let me ask you one question to you all. So what are the typical values of the axion mass that we have heard in the lectures? How heavy is the axion? Can someone tell me?
Hello.
No one?
Yeah. Can you hear me? Maybe.
Yes, sir.
I guess something like 10 power of 9 GeV.
Sorry, could you repeat? How much?
10 power of 9.
No,
GeV.
okay, so 10 to the 9 GeV is the order of magnitude of the axion scale, right?
Oh.
But this is not the axion mass, right?
Okay.
However, so this is the axion scale with its super large. However, the axion mass, MA, is typically of the order of micro electron volts or milli electron volts, anyhow, super light. And we can see it, for example, here in these plots that we were showing, right? Let me put it up here. So as you can see, so it is true that what you were saying, that the axion scale FA can be of the order of 10 to the 9, right, for example, but the axion masses that you see here in the x-axis are super low. Axions are really light particles, right? However, I'm sure that you have heard that a lot of people saying that dark matter cannot be too light, right? So a lot of people, you have heard that that, for example, neutrinos cannot be dark matter because they are too light, and therefore they are still relativistic at the time of the CMB, and therefore they are not good dark matter candidates. However, we keep telling you that the axion is a good dark matter candidate. How come? So the reason is the production mechanism. The reason is that typical dark matter candidates like the WIMP are thermally produced. This means that they were in thermal contact with the standard model, and then they freeze out, and we obtain a relic density of dark matter WIMPs. However, in the case of the axion, the production mechanism is completely different. It's what is called a non-thermal production mechanism. And in particular, there are several ways of producing the axion, but in these exercises, we're going to focus on one of them, that is the so-called misalignment mechanism, right? That we will see that in general, a scalar field with a potential that evolves in the early universe will be produced in large quantities, right? And the key is that in order for the axion to be dark matter, we need to produce it in large enough quantities for it to comprise all the dark matter density that we observe in our experiments. So, okay, so here in the exercise, what it is asked is to study the equation of motion governing the evolution of the axion, right? In particular, so this is the equation of motion of the axion in the case in which the axion field is homogeneous, right? So it does not vary in space. Of course, it will evolve in time, but we're assuming here that in every point of space, the action field is exactly equal. So before going on, let me clarify one thing of notation. That is that in this lecture, I'm going to use theta defined as axion over Fa. Okay, so this will be a synonymous of the action field. So theta now is not the theta parameter, but it is actually a scalar field, right? Theta is the axion, okay? So this is the axion. And then, not to get confused, so we are going to talk about cosmology, right? About how the axion evolves in an expanding universe. And in order to do so, we will have here the Hubble rate, H, right? So H is the Hubble rate that is defined as A dot A. But in this case, A is no longer the axion, right? A here is the scale factor of the universe. So in other words, this tells us about the size of the universe, right? So A in all these exercises is going to be the size of the universe. That's why the Hubble factor, which is the first derivative of A over A, is the expansion rate of the universe, how fast the universe is expanding, okay? Okay, so then once we have clarified the notation, we have here the mass of the axion field, which is the theta, and the Hubble parameter. Let's have a look at this differential equation. So this will govern the evolution of the axion field. And now my next question for you is, does this equation sound familiar? Can you recognize this equation that has appeared in any other point in your physics studies? Can someone tell me this equation of motion to which other mechanical system it could also correspond?
It seems a harmonic oscillator with a term.
Yes, exactly. So this is the harmonic oscillator with a frequency ma, right? In which we also have a friction term, right? So what the first thing that we can see here is that this is familiar and that the equation of motion is analogous to that of a damped. Oops, sorry. Harmonic oscillator, right? And in this case, what we'll have is that the mass is the frequency, right? And the Hubble parameter will play the role of the friction. So this is equivalent to the usual one that we usually have in this form, right? For a harmonic oscillator. So then this will be really useful because all the intuition that we have of the harmonic oscillator will be useful in order to understand the evolution of the axion in an expanding universe. Since of course you know how to solve it as a function of time, in the exercises I'm going to focus on see how all the different quantities evolve with respect to the scale factor. That means the size of the universe, because this will tell us the behavior of this axionic fluid, okay? So then, the exercise is asking us to solve these equations of motion in a really simple case, in a case in which the Hubble parameter is constant, okay, H equal to constant, and also the mass of the axion is constant. And moreover, we want to solve it in two different limits. First of all, we will solve it in the case in which the Hubble parameter is way larger than the mass, and then the opposite case. So let's start with... Okay, so let's start with the first case in which the Hubble parameter is way larger than ma. So in this case, the equation of motion is really simple. We can neglect the term with the mass, and we are left with this, right? And with this super simple equation of motion can be easily solved, but for example, if we have an initial condition in which the velocity, the axion velocity, is equal to 0, of course, one solution of this is theta equal to constant, right? And so this means that if we start with a given initial misalignment, this is what we will call initial misalignment. if we start with a given initial misalignment theta I, and we are in this regime, the axion field will remain completely frozen. That means that the axion field will be constant at a given initial misalignment value, right? Due to this Hubble friction, right? That is setting it in place. Then, of course, if we start with a theta, with an axion velocity that is different from 0, then we need to solve this equation, but this is super easy, right? I can define, for example, theta dot equal to x, and then the equation turns into this, right? Oh, sorry.
So the misalignment is the exact field structure initially.
Yeah, so actually, so it is called, okay, good question. It is called misalignment because this is the difference between the value of the axion field and the minimum of the potential, right?
Okay.
So,
okay.
so here,
okay.
yeah, so here I'm simplifying and I'm writing just a quadratic mass term, but actually in the full case, the potential for the axion, as we have seen, is a periodic. So we know that the axion is periodic,
Okay.
and therefore this will be something like a cosine, right? So in general, this would be, let's say, cosine of A over FA minus some theta QCD, right?
Okay.
So then what we call the misalignment is actually the difference. So let's say, so the theta I, right, it would be the difference between the value of the axion field initially, right, and this theta. But
Okay, it's
then,
clear.
at convenience, once you reabsorb this, it can be casted into directly the value of the axion field if you set as the origin the minimum of the potential.
Perfect.
Great,
Thank you.
thanks for the questions. Yeah, please keep asking. Okay. Okay, so we learned that if we start with 0 velocity, then the axion will be completely frozen at a given value. Now, if we start with some axion velocity, we turned into this differential equation that now again, if we take into account that h equals a dot over a, so from here you can easily see that this turns into dx over x equals to minus 3h dt, right? And now dt, I can turn it into minus, so h is this, right? So if I take into account that this is the derivative with respect to time, this is nothing but minus 3 dA over a. So finally, we have two logarithms, right? So we have logarithm of x over x0 equals minus 3 logarithm of a over a0, right? And finally, this means that theta dot, as a function of time or scale factor, if you wish, will be equal to a over a0 to the minus 3 times theta dot sub 0. Okay. So this is telling us that the general solution, if now we integrate this, you can do it carefully, but in general, the full solution as a function of time will be equal to the initial misalignment, theta sub 0, minus, minus the initial velocity times 1 over 3h times a0 over a to the cube. Okay, so the solution we have is that if I start with an initial okay, this should be, okay, sometimes I will use I, but sometimes I will also use theta 0. Okay, I will try to keep it consistent. So this would be I. So this is telling us that even if I start with some velocity, this will be soon redshifted, and at the end, the axion will be frozen, right? So at the end, at large times, this will be equal to constant. So the conclusion that we get is that in this regime, the axion is frozen at a constant value due to Hubble friction, okay? And this is the first part of the exercise. Then And the second part of the exercise is to solve this differential equation in the other limit, right? In the limit in which h, the friction, is way smaller than the mass. So, okay. So now let's go to the second case in which h is way smaller than the mass of the axion. So let's write again the equation of motion, right? That this is nothing but this plus 3h theta plus ma squared theta equal to 0. Okay, so then if this term is really small, how is the solution going to be, right? So we know that if we completely neglect the friction, we have a pure harmonic oscillator that, of course, we know that we can solve with an oscillating function, right? So an exponential with a frequency that equals the axion mass, right? However, we will have some friction, right? So the friction, what we'll do is keep reducing the amplitude of the oscillations, right? So in order to obtain the exact dependence of the of how the amplitude goes down with due to the friction, what we can do is to use the following ansatz. So we know that we will have a piece that is oscillating with a frequency ma, and then we can put here an arbitrary time-dependent amplitude for these oscillations, right? But then moreover, since we know that this term, that h is way smaller than ma, we are also going to use that the rate at which this amplitude gets smaller and smaller is slow as compared to the oscillations. This means that we will use what it is sometimes called the Adiabatic or Wkb approximation, in which b dot over b is way smaller than ma, and also b dot dot will be over ma will be way smaller than ma. Okay. So now what we can do. So now what we can do is just compute theta dot, right? That this is going to be equal. So as we all know, let me just derive, right? And we'll get here b dot plus ima times v. And now we can also compute dot dot, that this will be equal to b dot dot that we're going to neglect due to this, right? And then we'll have times 2 ima b dot minus ma squared b. Okay, now we can put everything together and again neglect this factor because this is going to be well smaller than ma, so we will also neglect this. And when we put it all together, what we find is a new differential equation for this that will be b dot plus 3/2 of h times b, and then we'll have minus ma squared b from here plus ma squared b equal to 0. So this goes with this, and we get this really simple differential equation for the amplitude, right? And this is really easy to solve. Again, if we remember that h equals dA dt 1 over a, we can plug this in here. And again, what we get is that dB over b equals minus 3/2 dA over a. And as a conclusion, we know that the amplitude of this oscillation will be equal to some initial amplitude b0 times a over a0 to the minus 3/2. Okay. And now we can go back that what I'm calling here B0 is nothing but the initial misalignment, right? So I can write here theta initial, right? And then if I put together this time-dependent amplitude with the oscillation, the final result is that the evolution of the axion field is going to be equal to theta 0, a over a0. Sorry, let me move this. to the minus 3/2 times cosine of MA T. Okay, so finally we have the solution of our equation of motion. So this is going to be the evolution of the axion field in an expanding universe with a scale factor A. And what we see is that the axion field will be completely homogeneous, right? And it will oscillate with a frequency governed by the mass of the axion. And the amplitude of these oscillations will be redshifted as a to the minus 3/2, okay? Okay, so now we have the solution for the axion field, but in order to get a better flavor of what kind of fluid is this axion, what we need to compute is the energy density and the pressure. And once we know how the energy density redshifts, we will be able to understand why the axion is a good dark matter candidate. Okay, so the next part of the exercise is asking us to compute the energy density and the pressure of the axion, right? And here we have the expressions for the energy density and the pressure. And in this case, as I was telling you, since the axion is basically a field that it is oscillating with a frequency MA, right? It will be crucial that in order to compute the pressure and the energy density, we will need to average over many oscillations, because we know that in this regime in which the axion is already oscillating, the frequency of the oscillation that is governed by MA is way faster than the expansion rate, which is h. This means that the axion is oscillating pretty fast, and effectively in terms of energy density and pressure, what we are interested in is in the average, right, over many oscillations. Okay, so now let's compute the energy density and the pressure of the axion. In order to do so, the only thing that we need to do is to compute the first derivative. That will be nothing but θ0 MA A over A0 to the minus 3/2 times cosine of MAT. So this comes just from making the derivative up here. So now another question. Am I missing any other piece? Are there more terms here that I should take into account when doing the derivative with respect to time of all this? So if you realize, here we have the explicit dependence on time. But the universe is expanding, right? This means that A also depends on time, right? However, the terms that we will get here will be, since the derivative of the scale factor with respect to time is basically A times h, the terms that we will have here will be of the order of h over MA, right? So then in the limit that we're considering, we will neglect them, and therefore theta dot will have only this expression. Now, once we have the theta dot, we can compute the axion relic density, right? Let's write this over Fa. And this is nothing but the kinetic. So this is rho kinetic, right? The kinetic energy that is related with the axion velocity plus the potential energy that is related with the mass of the axion, right? So if we substitute these expressions here, what we get...
Sorry?
Yes?
Can you hear me?
Yes.
But sorry if I interrupt, but shouldn't there be a sign instead of a cosine in the derivative?
Oh, you're completely right. That was a typo. Thank you very much. Yeah. So this is wrong. This is a sign. Exactly. Thank you very much. Because otherwise the following result was not going to work. Yeah. Thank you very much. Yeah, that was a typo. Yeah. Exactly. So then now once we take into account this theta dot and this theta, right, we can put it together in here, the kinetic and the potential energy. And what we get if we take out the common factor is that this will be equal . So we have basically here the same amplitude step for MA, right? But in theta, we have it multiplied by MA squared. And in the theta dot, we have already the MA. So then we can pull out this factor, right? And then the only thing that is different in the kinetic and in the potential is that in one case, as your colleague was commenting, we will have, in the case of the kinetic, we have the sine squared of MAT, and for the potential, we will have cosine squared of MAT, right? And of course, this is equal to 1, and this means that this is the energy density of the axion field, okay? Now let me compute so now if I want to compute the pressure, what I can do, so now if I want to compute the pressure instead of, if I want to compute the pressure, then here I have the pressure of the axion over Fa, and the only difference is that here I will have a minus, right? So instead of a plus, right? Because as you can see here, the formula of the pressure is exactly equal, but with a minus sign here. So in this case, we already have the solution that is only this one here, right? And in this case, what we can do is make an average over many oscillations, as I was telling you. Since the expansion rate is slow as compared to the oscillations of the axion, what we care about is the average over many oscillations. And if we make the average of all these over many oscillations, right? Let me put it here. We of course get 0. So then the conclusion that we're getting is that this axion, even though it is an oscillating scalar field, it behaves exactly as non-relativistic matter, right? Why? Because it has no pressure, right? And moreover, it dilutes, oh, by the way, this was also another typo, this would be minus, right? That we have here. So it has no pressure, and it redshifts as non-relativistic matter, like a⁻³ in the same way that if you have a number of balls, the density, when you increase the size, goes down with the cube of the size. What we're getting is that this weird fluid that is basically an oscillating scalar field also redshifts as a⁻³. And this is why the axion is a good dark matter candidate. Since the Relic density goes like a⁻³. It is important to note that even though the redshift, the behavior of the axion is the same as non-relativistic particles, as dust, actually, fundamentally, is a completely different dark matter candidate, right? Because it's not that we have different axion quanta that are basically like different balls in a space that are getting diluted. The physics is completely different. What we have is an oscillating scalar field that happens to redshift in the same way as matter does. So actually, even though we call this dark matter, this is more of a wave like dark matter, okay? And as a consequence of this, the ways in which we detect the axion or we try to detect the axion are completely different with respect to other standard dark matter candidates, such as the WIMP and other candidates, right? And okay, and here I just wanted to show you the numerical solution of this equation of motion. And as we were commenting at early times,
Excuse me, can I ask a question?
Sure, yeah.
But if it is homogeneous, can it explain, for instance, the rotation curves of the galaxies? I mean,
yeah,
is it compatible with oscillation or with observations?
Yeah, that's a good question. So this is at the moment in which you produce it. Okay, first of all, I have to say in the misalignment mechanism, and I'm not telling you, but this would be one of the particular scenarios that would be the pre-inflationary scenario, right? But anyhow, at the time at which these oscillations are created, the axion field is completely homogeneous, right? However, this has energy density, and therefore, since there's energy density stored, this gravitates. And what will happen is that the action field will not be completely homogeneous, and there will be some fluctuations that make that in some points of space-time, we have more energy density than in others. And then once you turn on gravity, you will see that this will collapse in the different halos that we have now in all the different galaxies. So this is a really good point. So for when you try to compute the relic density and you try to know how much energy density is stored in terms of axions, you start with a almost homogeneous field, but then the evolution, once you take into account gravity, will make these actions to collapse in structures that will be the seed for then the galaxies and all the structure that we see in the universe. So that's a good thing. Currently, it's at the scale of the universe, it is not completely homogeneous, but the dark matter is, of course, concentrated in the galaxies and where we have also baryonic matter, right? Okay.
Okay, thanks.
Yeah, but good question. Yeah. Okay. Okay, so how am I going with the time? Okay, so okay, so what I'm going to do, since okay, the next exercise was suggesting to make a change of variables, because okay, until now we have been solving a really simple equation, that is the one we have here. In the one that we have here. Okay, now I cannot see anything, sorry. Okay, this differential equation in the limit in which the Hubble parameter is constant and the mass is constant. However, this is not a realistic case, because in the case of the QCD axion and in the case of the Friedman-Robinson-Walker cosmology, both things vary with time. Both the Hubble parameter and the mass of the axion will evolve in time. And this is why this solution is not completely correct, right? But tell us the qualitative behavior of the axion. In full generality, what you need to do is to solve the differential equation for generic H and MA. And in order to do so, it's typically really convenient to perform a change of variables and turn the static differential equation into this other differential equation. And with this, it is way easier to use the so-called Wkb approximation or the Adiabatic approximation that we all have used, I don't know, to compute tunneling or also for the harmonic oscillator. But I think that I'm going to skip this exercise because I think it will be more useful to look at the next ones, right? But I can tell you, I can give you the answer later on if you're interested on it. Okay. So as I was telling you, after turning the differential equation into this other one can use the so-called Wkb approximation, in which we assume, as we were saying, that the amplitude evolves slowly as compared to the oscillations, right? So this means that MA is way larger than the time dependence of the amplitude. And if you use this approximation, you can obtain that in full generality for any universe, right, irrespectively of whether it is radiation dominated or matter dominated, and also for any dependence of the axion mass, this is a good approximate solution, in which we see that still the axion field redshifts as a to the -3/2, right, as you can see from here, right? And we also see that the axion is oscillating with a frequency that depends on the mass of the axion. Now it is not only ma times t, but we have this integral, okay? But anyhow, irrespective of the specific behavior of this function, what this exercise is asking is to show that this quantity, that sometimes is called the co-moving number of axions, is an adiabatic invariant, right? So we want to show that NA dot equals to 0, right? And this is sometimes called the co-moving number of axions, because basically what you're doing is taking the energy density of the axions, you multiply it by the scale factor, right? So the density times the volume, it gives you the total energy, let's say. And then this total energy, you're dividing it by MA, right? That could be thought as the energy of one axion quanta, right? So in some sense, this quantity, that's why sometimes it is called co-moving number of axions, which will be constant in the evolution of these axions, right? So in order to show this, we will use one property of this solution, that is that the kinetic energy is going to be equal to the potential energy. If you remember, this was exactly what we showed in this other simple case, right? If we make the average of the sine squared, we get the same as the average of the cosine squared. So that's why from here, we could have obtained that the average kinetic energy density equals the average potential energy density, and it's nothing but 1/2 of the total energy density, right? So now in this general case, this equipartition of the energy of the potential and kinetic energy density will also hold, okay, even though the specific dependence has changed a bit, this will still be true. So now what we want to compute is how much is the NA over dt, right? And this is the dt rho a cube over ma, and this is nothing but a to the cube over ma times energy density dot plus energy density times 3a dot over a minus m dot over m. Okay, so this is the derivative of this quantity, and we want to show that this is equal to 0, right? This is what we want to show. So in order to do so, we need to compute theta dot, right? So sorry, we need to compute the time derivative of the energy density, right? And let me divide by Fa. And so, of course, you remember that this over Fa squared equals 1/2 theta dot squared plus 1/2 ma squared theta squared, right? So now if we make the time derivative of this is nothing, okay, this should be a squared, and this is nothing but theta dot times theta dot dot plus m dot times theta squared plus m squared theta dot, right? So this is the time derivative of the energy density. But now here we can use the equation of motion, right? And we know that during the evolution, theta dot dot plus 3h theta dot plus ma squared theta equal to 0, right? So from here, we can substitute theta dot dot in terms of theta dot and theta. And therefore, if we do so, this turns into minus 3h theta dot squared, right? Because we multiply this times the theta dot, right? Then we have minus m squared theta dot, sorry, theta dot plus m dot theta squared plus m squared theta dot. So what we see is that this goes away with this, and the conclusion that we're getting is that the time derivative of rho is equal to minus 3 a dot over a times theta dot squared plus m dot over m times m squared theta squared, okay? Okay, so now the only thing that we need to do is to substitute this time derivative in here, right? And if we do so, and of course we can easily recognize that this theta dot is related, right, with the kinetic and this m squared theta squared will be 2 times the potential, right? And this will be 2 times the kinetic, right? So then once we put all this in together into the dNA dt, it is really easy to obtain that which will be equal to a to the 3 over m times 3/8 plus m dot over m times potential energy density minus kinetic energy density. And of course, as we said at the beginning, we know that during the evolution, if we make the average over many oscillations, this is nothing but 0. Okay, so by doing this, we have been able to show that Na, this common number of axions, is completely constant. And therefore, we will be able to, so in order to compute how many axions, right, how big is the energy density in terms of axions, we don't need to track the whole evolution of the axion, but we can just compute this quantity at the beginning of the oscillations, and then we know that this quantity will be completely equal nowadays. And therefore, in this way, we can compute how much is the axionic relic density today. Okay. So, okay. So now let's go to the next exercise, in which exactly what the exercise is asking is exactly to compute the current axionic relic density as a function of the initial misalignment, the axion mass that in general can depend on temperature, and therefore we need to evaluate as a function of the current axion mass and the axion mass at the time of the beginning of the oscillations. And then this will be also as a function of the temperature of the universe and Fa, right? In order to do so, we're going to neglect the number of degrees of freedom in the expanding universe. We're going to assume that this is equal to 1. And therefore, we're going to use the Friedman equation that tells me how the Hubble parameter evolves as a function of the temperature of the thermal bath. That is this one, in which we have already applied that the number of degrees of freedom is equal to 1. Okay, so as we have already commented, we know that then the qualitative evolution of the axion will be that at early times here, so here I'm plotting as a function of temperature, but we know that, so this means that time evolves in this direction, right? And then temperature here, this is large temperature, and this is low temperature. So I invert the sense of the temperature in this plot, right? So this means that the time evolution goes to the right, and to the right we go to smaller and smaller temperatures, right? So at the very beginning, when the universe is quite hot, the Hubble parameter is really large, and therefore there's a lot of friction, right? There's a lot of friction, and the friction is way larger than the axion mass. This means that the axion is frozen at this initial misalignment. Then we reach a point that we will define as temperature 1, T1, at which the Hubble parameter is of the order of the axion mass. And at this moment, the axion starts to feel the potential and starts to roll to the minimum of the potential. So it is at this moment in which the axion starts to oscillate around its minimum. And from this moment on, we can use these approximate solutions that we have been developing. So this means that at the very beginning, we can use that the theta was completely constant, but then from the moment in which the axion starts to oscillate, then we can use that this co-moving number of actions will be constant, and therefore we can use this in order to compute the relic density. Okay, so then what we want to do is that the energy density, so this adiabatic invariant, this co-moving number of actions was equal to energy density times a to the cube over ma, right? And we know that this whole thing is going to be, oh, sorry. This whole thing is going to be equal at T1 and now, that we're going to call it T0. So in order to obtain the energy density today, what we will do is first compute this quantity at the moment in which we know all the parameters, that it is at T1, right? And then we will use the conservation of this adiabatic invariant in order to obtain the energy density today. So this means that this adiabatic invariant at T1 can be computed because, if you remember, we know that the energy density is going to be equal to Fa squared times 1/2 theta dot squared plus 1/2 ma squared theta squared, right? So now if we evaluate the energy density here at the very beginning, what we know is that theta dot equals to 0, right? So we can remove this, right? And then, so if we want to compute it at equal to 1, right? So this is 0, and then the theta is nothing but the initial misalignment, theta I, right? So then we know that this invariant that we have here is nothing but 1/2 of m1 squared theta I squared. Yeah, of course, by the way, here, if we want to evaluate it at T1, this mass depends on the temperature. So actually here we should put also m1, right? So this is m1 squared theta I squared times Fa squared. And then we're going to define A1 as the scale factor at the temperature T1, okay? A1 to the cube. And all this, we have to divide it by M1, right? Because we have here, everything has to be evaluated at T1. And all this, of course, here we can do this. And this will be equal to the energy density today, that we're going to call it sub-0, times the scale factor today to the cube over the mass of the axion today. So finally, from this, we can obtain that the energy density today is nothing but 1/2 of m0, m1, theta I Fa squared times A1 over A0 to the cube. So then the conclusion that we're getting is that we had some initial energy density that depends, of course, on the mass of the axion and on the initial misalignment. And then in order to compute the energy density today, we need to take into account this so-called dilution factor. And then we have the formula of the relic density in terms of these scale factors. However, in the exercise they are asking for us to compute this, but not in terms of the scale factor at A1 and the scale factor now, but we want to compute it in terms of the masses of the axion at different temperatures, and at most the temperature of the universe today, right? So in order to do so, what we can do is take into account that in an adiabatic expansion of the universe, we know that the comoving entropy is conserved. This means that if we define this comoving entropy as the entropy density times A cubed. This is nothing but 2pg, the number of degrees of freedom, times T cubed times A cubed over 45. This will be constant, right? But since we are in this limit in which we are saying we are neglecting the number of degrees of freedom, we are saying that this is 1. The conclusion that we get from here is that during the evolution of the universe, temperature to the cube, A to the cube, equals to constant. Okay? In particular, this means that if now we want to compute this dilution factor, which is A1 over A0 to the cube, this will be nothing but T0 over T1 to the cube. And therefore this dilution factor, now we have it in terms of the temperature of the CMB today, T0, and the temperature of the universe at the moment in which the axion started to oscillate, T1. But now, how do I compute T1? So we know from the exercise that is already giving us the relation between the Hubble parameter and the temperature of the universe. This is telling us that h squared equals T squared over M Planck. And now what we want to know, so this means that T1 will be equal, oh, sorry, I think here there's something. Oh, sorry, here I have a typo, right? So this is wrong. This should be h, not h squared, okay? This is a typo, sorry, I will correct it in the exercises. This should be h, not h squared. And as a consequence, this is not, well, this I can remove, sorry. And therefore, now the units are correct. And what we get is that T1 is going to be equal to the square root of h at T1 and M Planck. But now, what's the value of the Hubble parameter at T1? If you remember, we defined T1 as the moment in which the Hubble parameter is of the order of magnitude of the axion mass. This means that h at T1 is nothing but M1. So then here, this means that T1 equals to a square root of M1 M Planck. So now, putting all together, we arrive to the conclusion that the axion energy density today is equal to 1/2 square root of M0 times M0 over M1 times T0 to the cube over M Planck to the 3/2 times the initial misalignment FA squared. And this is the final result. As we can see, the energy density of the on axions depends on the axion mass, and the larger the axion mass, the larger the energy density. But most importantly, it depends on the axion scale. The larger the axion scale, the larger the energy density in axions. But moreover, we can see that we can enhance the Relic density of the axions by having some temperature dependence. So if you see here, as compared to the case in which the axion mass is constant, effectively what you are doing is changing the onset of oscillations. If the mass is smaller at high temperatures, we are delaying the onset of oscillations and therefore enhancing the action relic density. And okay, and with this, I think I am done with the exercises. So is there any question regarding this exercise or the lectures?
I haven't understand if in the current universe the mass of the action is constant or not.
Sorry, could you repeat?
In the current universe, the mass of the action is constant or not?
Ah, yes, okay. So yeah, in fact, I just wrote this without explaining anything at all, right? But in fact, one can compute, in the case of the QCD action, one can compute what is the temperature dependence of the action mass, right? And in particular, so this can be done in the lattice, and also there are some estimates that come from the so-called dilute instant-on gas approximation, right? But in general, the bottom line that you need to remember is that the mass of the action as a function of temperature equals to when the temperature is way smaller than lambda QCD, the action mass is constant. And is the usual formula that we all know of m pi, m pi, f pi, m up, m down over m up plus m down. This is the mass over Fa. This is the mass of the action at low temperatures, right? So that's why in our current universe, the mass of the action is constant, right? And since lambda QCD, it did not evolve in time. However, at large energies, we know that the mass of the action gets suppressed by a factor lambda QCD over temperature with some power that is of the order of 4 times MA at T equals 0 if the temperature is larger than lambda QCD. So that's why when I was plotting here as a function of the temperature going in the other direction, I was showing that that typically what we expect is that the mass of the action grows, and then at lambda QCD, it saturates to this value MA0. Okay, so this is the evolution of the action mass. And in fact, this is important, right? This is, for example, one of the inputs that we have in action cosmology from QCD, in particular from lattice QCD, right? Because if you really want to compute the action relic density really precisely, you need to know exactly when the action starts to oscillate. You need to know this T1. And in order to know T1, you need to know the mass of the action here as a function of temperature, right? And in order to do so, you basically need to compute the topological susceptibility of QCD, right? And this is what people compute in the lattice, that even though it's really heavy computations, right? But they are able to get some results, right? And this is actually how we get right now the best estimates of the action relic density in terms of this misalignment mechanism. So was it clear? No? So this is the question was, how is the temperature dependence of the action mass? In the case of the QCD action, it follows this dependence. Is there any more question?
Yes, the fact of having neglecting the time dependence of the effective number of degrees of relativistic degrees of freedom. I mean, it was just a choice to get a nice compact formula, or is it also justified from a physical point of view?
Yeah, so really good question. So this is, so in order to compute the correct result, it is not justified. I did it because otherwise this formula becomes a complete mess with a lot of ratio of the different degrees of freedom, right? But of course, in order to compute the correct relic density, you also need to take into account that. And it is also there where also lattice QCD is really useful, because in order to compute the temperature dependence of the number of degrees of freedom, when we are close to lambda QCD, we need to use the lattice. So yes, it is crucial in order to obtain the result. But of course, for the exercise, I prefer to simplify it, not to get lost with all these factors that make the final result a bit more ugly. Yeah.
Thanks.
Is there any more question or comment?
Maybe a comment more than a question. The fact that we have a particle whose mass depends on time and temperature. I mean, we are usually used to have mass particles with a constant mass, and it sounds strange. I don't know. Whoa.
Well, actually that's not the case, right? So when you have a thermal bath, quite often particles get thermal masses, right? So if you have a bath of electrons, even the photon develops a thermal mass, right? So it is quite common in when you have a thermal bath for the masses of the particles to depend on the temperature of the thermal bath. In the case of the axion, is a bit unique, right? Because so in the usual case, the larger the temperature, the larger the mass, right? In the case of the axion, this is not true, right? And this can be related with the fact that if you remember, the axion mass came from the coupling of A to gluons, right? And from this, we can get an understanding of why the axion mass becomes smaller and smaller the larger the temperature. The reason is that we know that alpha S for temperatures going to infinity goes to 0, right? And here we have the alpha S, right? This is why for large temperatures, the axion mass becomes smaller and smaller because QCD becomes more weakly and weakly coupled. And this is why for high temperatures, we have a smaller mass of the axion, while at low temperatures, at the end, we have the confinement of QCD, right? And then we can compute with the chiral Lagrangian the mass of the axion, which at the end, it becomes almost temperature independent. Yes. But this is not unique to the axion, what I'm saying. So in general, particles can have a different mass in a thermal bath.
Okay, thank you.
Is there any more question? Anyhow, you have, I send you again in the chat the exercises and you have my mail. So if you have any question, maybe looking again at the exercise or whatever, feel free to write me a mail. And okay, and I think that with this I am done. So let me stop sharing.
So, Pablo, thank you for these beautiful exercises and for the fact that you will remain available for the students. Thank you.
Yeah, thanks for you for the invitation. I'm happy to be here.